Let's look at two sequences of numbers. So the first will be the Fibonacci sequence that you may already be familiar with. The way it works is we either start off typically with 0 and 1 or 1 and 1, but we'll do, for this example, the 1 and 1. And so once we have these two numbers, then each additional number is the sum of the previous two numbers. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, then we have 13, 21, and so forth. All right. For our second set of numbers, let's say that we invested $100. And we invest it into something that pays 5% interest per year. And so if we look at what we would have, and what's in the amount column will be the sequence. In year 0, that's our initial $100. And then at the end of that year, or beginning with year 1, then we'd have 100 plus 5% of that, which is $5, for a total of $105. Now, if we leave the $5 in there and earn 5% on the $105, then we have $110.25 for the second year. And then the third year, this would be $115.76, and this is rounded off. And we could continue, just like here we could continue. So we have these two sequences of numbers, and the way that I produced each of these that you just saw, I used what's called an iterative approach. Iterative. Okay? So I just iterated through some process in which I started with some values, and then understanding the relationship, I then produced the additional values. The problem with that, though, is one of scalability, okay? Because often I want the nth value, and I don't want to produce the n minus 1 previous values. So if I simply wanted to get, like say in the second case, if I said, well, how much money will I have at the end of 10 years, or beginning in year 10, how much money will I have? Well, we don't want to have to produce all these other values. One reason would be we probably don't really care about them, but the more significant reason, is that it's a very computationally expensive process to do if I'm doing this for a large amount of n, okay, or for a large value of n. 100, you wouldn't want to do this by hand if I said go to 10 or 20 years or even 100 years. What if we said 1,000 or 1,000,000 or something like that? Of course, for the second problem, doesn't really make sense to worry about what you'd have in 1,000 years, but certainly you might want to know what the 1,000th Fibonacci number is. And so it can become a very computationally expensive process, which in turn means lots of time. So instead, what we would like to have is what's called a closed form solution. And what that is just a formula, or maybe a function of n, that allows you to put in the value you're interested in. Like for year 10, I could plug in 10 here and have it give us the result. Now in the case of the Fibonacci sequence, believe it or not, the closed form solution is this. F of n is equal to square root of 5 over 5 times 1 plus square root of 5 over 2 raised to the nth power minus square root of 5 over 5 times 1 minus square root of 5 over 2 raised to the nth power. Okay, so this is for Fibonacci. What about the second problem? For this particular case, where I'm using 105%, then A of n is simply equal to 100 times 1.05 raised to the nth power. The more general form of this that you would see in a book would be if 100 is, say, P, our principal, and 5 is R, our interest rate, well then it becomes P times 1 plus R raised to the nth power. So where do you get these closed form solutions? Well, each of these sequences can be defined recursively, okay? And what that means is that they're defined based upon previous values. So that leads to this right here. A recursive definition is one in which a value is defined in terms of one or more previous values, right? For Fibonacci, we use 2 previous values. For the investment problem, we only use 1 previous value, which means for a recursive definition, we need 2 things. We need a basis. That's the one or more initial values that get the process started, right? What were the initial values for a Fibonacci sequence, 1 and 1? What was the initial value for our investment? That was $100. And then we have a recurrence relation that relates the current value to one or more previous values, okay? So for Fibonacci, then we have the basis was that f of 1 was equal to 1, f of 2 was equal to 1, and then the recurrence relation was that f of n is equal to f of n minus 1 plus f of n minus 2. Now, if you look at this online or in a book, sometimes you'll see these written as subscripts. So this would have been f sub 1, f sub 2, and this would have been f sub n is equal to f of n minus 1 plus f of n minus 2. It doesn't really matter on that, okay? For the investment problem, we have a basis of this. For this particular problem, our basis was that a of 0 was equal to $100, and a of n was equal to the 1.05 times, 1.05 times a of n minus 1. So 1.05 times the previous value. F of n here is equal to the previous value plus the value before that. So the Fibonacci, because it uses 2 values, is called a linear second order recurrence relationship. The investment problem is a linear first order recurrence relation. Do these definitions really work? Let's check a couple of values and see what happens. So we had f of 1 was equal to 1, f of 2 is equal to 1. So f of 3 is equal to f of 2 plus f of 1, which is 1 plus 1 equals 2. F of 4 is equal to f of 3 plus f of 2, which is, f of 3 is this right here, the 2, so 2 plus 1 equals 3. F of 5 is equal to f of 4 plus f of 3, which is equal to 3 plus 2 equals 5, and so forth. So that works. We can see that's what's happening. In fact, that's what I did when you saw it at the beginning of the video. Right? What about the investment problem? A0 is equal to 1. A1, or 100, excuse me. A1 was equal to 1.05 times 100, which was equal to the $105. A2 is equal to 1.05 times our 105, which was equal to 110.25. A3 was equal to 1.05 times 110.25, which rounded off was 115.76. And we could continue this if we wanted to. So when we see those work, how do we use the recursive definition to produce the closed form solution? That's what we'll look at in the next video. We're only going to look at the first order type of problem because it's much easier than the second one. But we're going to use a process called expand, guess, and verify. And that's what we'll do in some examples in the next video.